we are fortunate to have as our presenters today Amir Hakami from the Department of Civil and Environmental Engineering at Carleton University, as well as Robin Chatwin-Davies.
Okay, thank you, Mary. I assume you can hear me well. Thanks everyone for being here. I think I hope this medium of presentation is it works well. So Robin and I are here to talk about different ways that we can use air quality models to link various policy endpoints such as health, climate, and environmental justice together. It's a work by a number of the students at Carleton or postdocs at Carleton, Robin included. Angel Généraux is another student who has material on this presentation, but isn't presenting today. Marginal, Sultan Zadeh, Shunli Zhao, Barako Stanner, Megan Keon, Amanda Papin, who's at Health Canada now. Last but not least, a number of researchers in the U.S. and Europe contributed to development of tools that we use to conduct a study. Next slide, please. So as I said, we want to see how we can use models to guide decisions and policy development, and how we can use different analysis tools that are implemented in these models to provide what I call decision metrics, quantitative numbers or metrics that can guide the decision-making process, and particularly how we can do that in a way that links different endpoints and gets closer to an overall view of integrated assessment, something that CANUE is very much built on. Next slide, please. So if we look at those three endpoints that appear in the title, climate and health and environmental justice, I think you can imagine that there is a hierarchy of decisions, for the lack of a better word, maybe the level of political commitment to each one of those topics. Right now, in the political environment globally, I think climate has the strongest political wind behind itself, and partly probably because of the overall perception among politicians that consider the climate change to be a near existential threat. So it's one of those rare situations where there is the will, with some level of consensus, to do something. When you get to health and environmental justice, I think that level of political momentum and will is probably not as strong, and for various reasons that one can speculate. But the idea is that decisions that we make are going to affect these three areas and a number of other areas as well, regardless. So if we can find ways to align benefits that can be gleaned in each one of these areas through the same policy implementation, obviously that would be helpful, especially if we have the knowledge of what kind of actions would provide that level of alignment. Next slide, please. So what Robin and I are going to present is a very brief background to the methods that we use to conduct the type of analysis that we do, and then look at these three areas separately, but in relations with each other. And those areas being linking of health impacts to sources of pollution, linking or trying to coordinate climate control strategies or climate control measures, climate or greenhouse gas emission measures with air quality benefits, and finally linking some of the measures of environmental equity to emission sources as well. For us, this is more or less a new and ongoing area of work, and we definitely look forward to hearing your feedback and suggestions, particularly because CANUE has this unique spectrum and range to have experts and researchers in a number of these areas, but also in areas that we are not considering. So how we link on analysis methods, I assume everyone else is also having the slides. How we link our methods of analysis to decisions is really in recognizing the fact that the only thing that we can really realistically control to change the air pollution impacts are emissions. And we would like to use these models to quantify the impact that those emission reductions would have on different types of environmental or health endpoints. And that comes down to, mathematically speaking, to a sensitivity coefficient or derivative, that how changes in emissions would translate to changes in health or different types of impact. So the question does come down to calculation of sensitivities and derivatives as a measure of policy effectiveness. And these sensitivities, what they do is that if we do have them, then we can differentiate and distinguish between different measures that are presented to us as various policy options. So that's what we are hoping to do using air quality models. Next slide, please. And this is one example of the schematic that we use to do these calculations. We want to, for a number of endpoints that we look at, particularly on the health side, we try to monetize these health impacts, and we borrow from information and models and background data from economics, epidemiology, and air quality modeling. From economics, we borrow how value of the health endpoint, such as mortality, is identified through the value of a statistical life. From epidemiology, we use the associations between health endpoints, in this case mortality, and changes in concentrations. And then we use air quality models to link those changes in concentrations to changes in emission. If you combine all these pieces of information together, what you get is a monetized representation, monetized valuation of the monetized impact of changes in emissions or emission control. We call this monetized impact of health effects marginal benefits or marginal damages. This is a term that economists use and something that we consider to be an important decision metric because it would put the benefits of air pollution control on a comparable scale to the cost of making those changes. Next slide, please. And there are different ways to do sensitivity analysis. The more common way is what's referred to as forward sensitivity, and that's two different ways is to use models to propagate the impact of a source or number of sources forward in time and space to different receptors. So what you get is that how one single source or one group of sources would impact multiple receptors, and I like to refer to that as to using models to identify where impacts of sources travel to or go to. The method that we use is complementary to this. And if you go to the next slide, we refer to that as adjoint or backward sensitivity. It's the same type of analysis, but a different perspective. Now you start at a receptor or a group of receptors, and then you try to trace back the influences on that receptor or those receptors back to all the sources that can contribute to pollution in your computational domain. You do that by integrating a set of equations backward in time, hence the name backwards. But ultimately, the results that you get, what it represents is that where the influences on those receptors are coming from. So it's just a difference in perspective rather than standing at the source, looking forward and see where the influences go. You're standing at the receptor, looking back and asking the question where the influences are coming from. But it is useful, this approach, this alternative approach is useful because it gives you the ability to distinguish between the impact of individual sources. And it becomes apparent when I show some results. You can go to the next slide. So critical to doing adjoint sensitivity analysis is that definition of an objective function that we call adjoint cost function or adjoint objective function. This is the metric that we are calculating the sensitivity of. You want to see what is the impact on this thing. So in the very initial slide, when I introduce sensitivity as change in impact to change in emissions, this is the numerator of that derivative, the change in impact. That's what is the metric that you are looking at the impact on. And so long as we can come up, we can change or define a policy question to have two characteristics, we can use the adjoint method effectively to answer questions that are relevant to that policy topic. The first thing is that policy metric or that policy question we should be able to condense that into a single number. And secondly, that number should be a function of concentration. And there are a number of policy questions that fit that description. One of them, for example, is nationwide health outcomes, which is what we are going to look at first in our results. But other metrics like the amount of precipitation or deposition into a lake, or average concentrations, or maximum concentrations, or crop damage as a result of exposure to ozone. And as we see later, inequality measures can also be defined in that sense. So here we are going to use mortality as our metric of interest. If you can go to the next slide. That description of mortality is obviously based on the data that we gather from epidemiology. And for the results that I will show, that data for Canada comes from mostly from a three-pollutant model representation that Rick Burnett and his group have been kind enough to provide us with, and in some cases also a single pollutant PM model. So most of the results are a three pollutant model, but some of the results, and I will indicate that, are a single pollutant model. And for the U.S., we're using the PM from Kruski et al. From American Cancer Society Reanalysis 2009 for ozone, Jarrett et al. 2009, and we're using also an NO2 representation, even though that work not constitute a significant NO2 impact. Just to be on the same page with Canada, we do that. Although I'm not really showing. I think I have removed most of the U.S. results. I'm not sure if anything is left, but if there are any U.S. results, that's where those numbers are coming from. And then we monetize the the health impacts using the value of the statistical life, which is a willingness to pay measure of what the society on a statistical level is willing to trade for reduced risk of mortality or death. Next slide, please. So first, we're going to look at health, and the idea is to try to assign the damage caused to each source of pollution at any location, at every location, or the benefits associated with reducing emissions from that location. You can go to the next slide, please. And these are the examples of the types of things that we can see. This, for example, is the marginal benefits or benefit per ton from reduced NOx emissions and the corresponding impact on reduced chronic ozone exposure and mortality. So let me just take a minute and explain what these numbers are. If you see a value of, let's say, $1,000 or $100,000 per ton at one location, it means that reducing 1 ton of NOx emissions at that location has a benefit as a result of reduced mortality in all of Canada equivalent to that number. So the benefit, so this is not a distribution of where the benefits are materializing. It's a distribution of how emissions at each location have impacts. So, and again, these are marginal benefits, meaning that you don't have to have emissions at a certain location to have a potential benefit from reduced emissions or a potential damage from additional emissions. Even if in places where you have no emissions, you can have this marginal benefit. But what you see is that there's a great deal of variability in the amount of benefits that you can gain from reducing emissions depending on where you are. And also in case of ozone, you do see negative numbers of what we refer to as disbenefits, which comes essentially from the titration of NOx by ozone in areas where NOx emissions are quite high, or urban areas mostly. Next slide, please. If you look at this is the same thing, but now it's NOx emissions, the impact of NOx emissions on NO2 mortality. And as you see, it's much more localized. It's much more limited to urban areas, and that's mainly because NO2 has a much shorter lifetime, so it doesn't really travel far. The health impacts of NO2 remain more local compared to that of NOx or PM. And the numbers obviously get large, and that's one important feature that if in Canada we prescribe mortality association to NO2, we get a landscape that is quite unique in terms of the NO2 signature. Next, please. And this is what you get for PM as well. Now, again, fairly local because this is primary PM emissions, but you can see that there are also quite a bit of long-range fingerprint on these emissions. So this is primary PM, but you can also get the same numbers for inorganic PM mortality, or the mortality associated with inorganic PM exposure that is secondary and comes from precursor emissions. So you can get these values for SO2, NOx, or ammonia as well. So again, to emphasize, if you see a number of $200,000 per ton, that means that reducing emissions at that location has that much benefit to Canada, not in that location, but to Canada. using the Adjoint method, what we do, the disadvantage is that we lose the ability to see where that benefit is happening. We need to complement the Adjoint with other methods of analysis to get that. Next, please. So there are a number of ways to use this type of information. Here I'm just showing a couple of examples. One is that we can look at those marginal damages or benefits and combine them with emission profiles from different emitters and come up with damage for each emitter, the amount of societal damage that are caused by each emitter. And one of these are what we call per vehicle health benefits that you can calculate for each vehicle. And if you segregate, or you distinguish between those by the age of vehicle and the type of vehicle, then an example of it would be what you will see in the next slide. So here you're seeing the damage caused by a typical vehicle of different age. So this is a light-duty gasoline vehicle, different ages. And as you see, the damage caused by each vehicle is obviously dependent on its age for various reasons, one being that the emission factors are different. They were built with different standards. So older vehicles are more damaging. On the other hand, older vehicles usually don't drive as much, so they have less mileage. Combining the two, this is the type of damage you get. And you can see that these numbers can get quite large, to the tune of a few $1,000s in large metropolitan areas. And again, this is a typical vehicle in that class. If you have an old vehicle, 14 or more year vehicle, it's quite possible that the societal damage caused by that vehicle is actually more than the worth of vehicle in dollar value. And go to the next slide, please. The same thing can be applied to other sectors as well. One other sector, for example, is residential with combustion. And when we apply this, this is one of those things that is quite surprising how big these numbers are, both in Canada but also in the U.S. So now what I'm showing here are not marginal benefits. They are the total benefits or the total health damage caused as a result of mortality that is due to or attributable to PM emissions from residential wood combustion. And residential wood combustion covers a wide range of things. It's not just the fireplace at homes. There are a number of a good size of households that actually use wood as a primary source of heating. If you add up these numbers, depending on what epidemiology you use, they can add up to very significant numbers. In Canada, that number can be anywhere between $7 billion for a 3-pollutant model to $30 billion per year for a single pollutant PM model. I mean, $30 billion is about 4,000 or so mortality. Next slide, please. So in summary, we can use the Adjoint to link health outcomes to emissions. And once you do that, you see that there's a lot of variability in both time and space. And I didn't show the temporal aspect, but there is a lot of variability in time as well, both day to day, but also diurnal variability, which is good in a sense because having that range of variability essentially provides the decision maker with potential value if the decisions are made in a targeted manner to go after locations or times that emissions are most damaging. And this is the whole premise of this talk, that we can have information that would enable us to differentiate between different types of emissions. One point of caution is that the benefits that we get depend on a bunch of things, and mainly epidemiology. And the work that researchers at Health Canada are doing, there's some really interesting work being done there, that looking at different ways of representing these risks, and the numbers that you come up with will depend on those representations. And that, as that field is fast evolving, I think this should really be looked at not as the numbers that I just presented, but as our ability, or as the existence of means to quantify those numbers. Next, please. So let's go to the interface or interaction now between health and climate, and we do that by looking at air quality health co-benefits associated with combustion-based CO2 reduction. Next, please. And the idea, again, is not novel. It has been there, and a lot of people have looked at it. What some of the methods that we are using would add is that you can look at co-benefits on a location-by-location basis. But the main idea is that drivers of air pollution and climate change or global warming overlap to a large extent. However, the policies that try to address these two issues are not always coordinated. In fact, they are rarely coordinated. And one way to coordinate those are through inclusion of co-benefits. And what to consider here is that for climate concerns, there is no differential benefit in reducing CO2 emissions from this source versus that source. Or this location versus that location. CO2 is CO2 no matter where it's emitted, for the most part. So the policy decision and choice comes down to the cost of control. What is more feasible and more economical to control? When you come on to the air quality side, the picture is very different, because there is a great deal of spatial variability between the impact of emissions depending on the location of the release. So your benefits, or air quality benefits associated with reduction of pollutants that come with CO2, have a very significant spatial component to them. If you include that spatial component, the decisions that you could make on the climate side, on the CO2 control side, could be very different. And those are the types of, again, information that we're hoping to be able to show. If you can go to the next slide, you see an example of that. Oh, not yet. But this is the same type of idea that we had before for calculation of benefits. The only difference is that the last term on the right-hand side is that in addition to the monetization with respect to emissions of pollutants, we can normalize those emissions to emissions of CO2 by sector-specific emission profiles of different polluters. Like, if you have a power plant, you know what a typical power plant, or any specific power plant, if you have the data, would emit in terms of NOx and PM emissions and SO2 emissions compared to its CO2 footprint. And combining all of those, you can calculate the dollar per ton of CO2 equivalent for different sectors. Next, please. And if you look at some of the examples of this, I'm showing transportation co-benefits in dollars per ton of CO2 emitted from transportation, and electricity generation from fossil fuels, and that includes both natural gas and coal. And by the way, these are simulations from 2007, so a lot of coal-fired power plants that are not in service anymore were still there. So the values that you see here, if you have $1,000 per ton of CO2 from transportation, that indicates that if you take enough CO2 emissions by taking the cars or improving efficiency or any other measure that would proportionally change the emissions of CO2 and NOx or PM or criteria pollutants, then the air quality benefits associated with that CO2 removal is going to be that much. And a couple of things that immediately come to mind is that these numbers are really large. They are much larger than the price of carbon in different markets. They are larger quite a bit than the social cost of carbon. So inclusion of air quality health co-benefits or health co-benefits really changes the landscape. The other thing to consider is that transportation usually is the larger contributor by far. So if you remove those few really high damage coal-fired power plants in Ontario, and if you primarily focus on natural gas transportation, there are a number of areas where transportation is more damaging on a levelized carbon basis. And that was for three pollutant model. If you actually go to single pollutant PM, these numbers do get larger. And again, there is that dependence on the type of epidemiology that you choose to represent these numbers. Next slide, please. And this is true for a number of sectors. It's hard to find a sector where air quality co-benefits are not significant. This, for example, is natural gas residential heating and a co-benefit in terms of dollar per ton for those, and they can get easily in the range of hundreds of dollars. Next slide, please. So the summary here is that these co-benefits are really significant, and they are significant enough to be considered, something that we are not really doing at a consistent level yet. The other thing is that transportation is the largest contributor, and the first thing that comes to mind is that if you can have a targeted approach to electrification of transportation sector, there seems to be very significant air quality health benefit implied in that. I have the total numbers for transportation and electricity generation numbers, but you have to remember that those numbers for electricity generation are only from fossil fuel electricity generation. So if you put the whole energy mix in there, those numbers, the average co-benefit is going to be quite a bit smaller. But also, if you remove the coal-fired power plants that are included in there, and they don't exist anymore, again, that number is going to be smaller for electricity generation. Next slide, please. So the next topic that we can add to this discussion is the question of equity and how our decisions can affect those. And I think I've talked enough, so Robin, I think can take this.
Hi, everyone. So I'm a graduate student with Dr. Hakami, and my research is focused on looking at the air pollution impacts on equity. If you can go to the next slide. So the field of environmental inequity or environmental justice more broadly looks at how environmental risks, in our case air pollution, are associated with socioeconomic status, such as income or race or education. And a lot of research in this area finds vulnerable populations face disproportionate health burdens from pollution exposure. And so our study is looking at New York City and the surrounding areas. We're focusing on the U.S. for now because we have very good data for New York. and we're looking at characterizing the inequity in air pollution across income groups specifically. And so we're trying to characterize the inequity, but then also to identify emission controls that can improve environmental equity through the adjoint modeling. And then we can contrast the sensitivities of the health and equity measures to coordinate those policies when managing air quality. You can go to the next slide. I'll talk briefly about how we actually are measuring inequity and inequality. One of the most common models used is the Lorenz curve, shown here as an idealized version on the left. And basically, you're plotting the fraction of people versus the fraction of your measure of interest. So in a situation of equality, you would expect, say, 10% of the people to hold 10% of the income, and so on, and that would be represented by the line of equality, the 45-degree angle, and the Lorenz curve plots the true situation of inequality. So in the case, if you're looking at exposure, we might find that 10% of the people are only exposed to 5% of the overall pollution versus the 10% most exposed are being exposed to far more than their share of the pollution. And then the Gini coefficient just refers to the summary statistic of the Lorenz curve, and it ranges from 0 to 1, where 0 is a situation of perfect equality, and 1 would be an idealized maximum inequality situation. And so what's important about the Lorenz curve is that this is measuring one dimension of inequality. So it can give us information about income inequality, or it can give us information about exposure inequality, but it's not necessarily telling us anything about the relationship between the two. So if you go to the next slide, we modified this slightly using something called the concentration curve, and that is looking at the relationship between income and pollution or health risk, where effectively what we're saying here, the line of equality is saying that we expect people, the 20% poorest people, when sorted by income, to be exposed to 20% of the health risk in a situation of equality. But what we might find when we plot a concentration curve is that, in fact, they are exposed to far more than their share of the health risk, looking at their income. And so the concentration index, much like the Gini coefficient, is a summary statistic that ranges from 0 to 1, where 0 is good, that's equality, and 1 is bad, that's inequality. And so we use the concentration index as our cost function in the adjoint model. If you can go to the next slide. So our study domain is New York City. We have a very fine resolution model, a 1 kilometer grid resolution. You can see it superimposed over the city of New York on the right, and we're focusing on a 2-week period in July. And then we're taking income data as 12-month household income, and then focusing on pollution from, much like the previous studies, a 3-pollutant model of NO2, ozone, and PM. So if you can go to the next slide. First, we looked at just the inequality in exposure to the 3 different pollutants. So you can see here, we see that there's inequality across all of the pollutants in varying amounts. So the most inequality seen is for NO2, and then ozone, and then PM 2.5. But this graph isn't giving any information about how this is related to socioeconomic status. This is just giving information about the inequality of exposure across the domain. And so in the next slide, you can see what happens when we look at that inequality across income groups. And so in this case, we're looking at the inequality in health risk experienced by different income groups. And we can see that NO2 and PM 2.5, there are higher levels of inequity of health risk exposure, and much lower levels for ozone, partially due to the longer lifetime of ozone across the domain. And these numbers are pretty close to what's reported in the literature for other urban areas in the United States. And another important thing to note is that we're assuming that the epidemiological impacts would be the same across income groups, which research indicates may not always be the case, but for this model, we've assumed a consistent concentration response function. And overall, we're finding that lower income populations are facing higher health risk than higher income populations across New York City. If you go to the next slide, so that was the forward results, just characterizing the current levels of inequity, but what is of interest is how we can reduce inequity across the domain, and so that's when we're using the Adjoint model and looking at the sensitivity analysis. And so in this case, we took the domain-wide inequity from before and looked at how that might change with a reduction in emissions. And so what this figure shows is that reducing, in this case, primary PM emissions in a specific grid cell would provide a domain-wide reduction in inequity. And so the positive numbers are good, meaning that reducing emissions reduces inequity, and that's driven by locations that have larger proportions of low-income people, and that has a larger impact on the domain-wide inequity. Negative numbers are bad, and it's saying that reducing emissions in those places would actually worsen inequity, and those are driven by locations that have high proportions of high-income people, and so reducing emissions there would make the situation more unequal across the domain. And so if you go to the next slide, as we've discussed before, inequity and inequality are only one part of many different policy metrics when looking at air quality management. And so we were interested in comparing the sensitivities of inequality to other endpoints. And so on the left is the same sensitivity of health risk inequality. And on the right, for the same domain, we're looking at, as discussed before, the marginal health benefits that can be expected from reducing primary PM emissions in any one location. And so to understand how these can be coordinated, we plotted the sensitivities on a scatter plot, which you'll see in the next slide. So we've plotted the sensitivities at each location, where the x-axis is the marginal health benefits, and the y-axis represents the benefits of reduced inequality. And so the goal is to identify locations where we carry both positive health benefits and positive benefits in terms of reducing inequality. And so those areas are highlighted in the green rectangle. But you can see that there are also many areas that, despite carrying positive health benefits, would actually worsen the situation of inequality in New York City. And so to visualize these locations, we came up with a scoring system based on the percentile of any given location, which percentile it falls in both data sets. And we've plotted that on the right. And so you can see the areas that are deep green are areas that carry high positive benefits, both for health impacts, but also for reducing inequality, versus you can see there are other areas that are in sort of cream color, where while it might carry positive impacts in one or the other, it might carry very low or even negative impacts on either health or inequality. And so this carries valuable information for managing air quality, because, for example, in the situation of New York, we can see that some areas would benefit from emissions reductions but would in fact make inequality worse, but that there are several other locations that carry similar health benefits, but would also at the same time improve environmental equity in the region. So you can go to the next slide. Just to summarize, so we can link what we see as the inequality or inequity to the different emission sources, and then we want to use that in tandem with other policy metrics to be able to identify emission reductions that carry positive benefits for both equality and other areas of concern. So I'll hand it back to Amir to wrap up.
Okay, and if you can go to the next slide, I'll try to wrap up. Just some general conclusions. So I think the main point that we've been trying to get across is that there is a lot of to be gained from being able to scientifically and on an evidence-based basis align the direction of some of the policies that we are going to implement, in particular climate policies, with health and environmental justice objectives. And we would be missing a great opportunity if we don't really do so, because there's great implied potential for harvesting those benefits. And we do have the tools to provide those decision metrics that can guide us in that direction. And here we only looked at air quality related issues, co-benefits, environmental justice with regard, or environmental equity with regards to air quality and health benefits in particular. But you can extend this beyond air quality to other mediums, but also other areas that would affect them. And I think CANUE is really well positioned to be the medium for that, to basically carrying that type of expansion. Next slide, please. Just quickly for future work, I think one question, and this is new for us, is what's the best way to present inequity and inequality, and how to best coordinate these numbers in that context. One thing that is very important, especially when you get to this type of urban environmental health, is availability of high-resolution data. And I think in Canada we are lucky that there is very good quality data sets available through the work that the region of Peel has done with RWDI in preparing such database for emissions and subsequent modeling. And they've been very generous in sharing that data for us, but that data is not publicly available. It would be great if we can expand on that data, but also find ways for the region of Peel, but also for CANUE maybe to facilitate its dissemination. And as I said, CANUE is really uniquely positioned to have a leading role in this. If you can go to the next slide. And all of these pieces are to bring us closer to that idea of integrated assessment, how you can analyze decisions in such a way that multiple endpoints are being quantitatively considered as you go forward. And for example, in terms of co-benefits, I think that's probably a pressing matter because those policies are coming forward, and it would be important to see if there is any practical place for air quality co-benefits to be included and integrated into various policy or economic instruments that are considered for climate mitigation. And if you can go to the next slide. I think that's it. A number of people, as I said, contributed to this work, but our acknowledgements also go to Rick Burnett and his group, Masoud Nassari and Lauren Pinot, for CAN check analysis, and also for New York Department of Health and ICF International for providing New York City data. Thank you.
Okay, thank you, Amir, for a very interesting talk, and Robin. All right, and do we have any questions coming up now?
This is Tim Tuccaro. Can you hear me?
Yes, we can.
Amir, thank you very much. That was really excellent, and your visualization is quite stimulating. I'm curious about any exploration you've made with non-mortality endpoints, so chronic disease endpoints, diseases like asthma, where people are affected at much younger ages, and so the lifelong cost is much greater than for mortality. Do you have some of these numbers, particularly the 3 pollutants and the co-benefits for morbidity endpoints?
That's a good question. So from some time back, we started focusing on monetization, and that's a controversial decision to have. But once you do monetization for various reasons, and that goes back to the way that the value of a statistical life is calculated, if you do that, mortality just dominates everything. So a while back, we looked at, for the U.S., not for Canada, but for the U.S., we looked at morbidity, and the mortality valuation accounts for more than 95% of the monetization. Now, that shouldn't really devalue the importance of other non-fatal impacts, and I think that's something that we should do and we would like to do. The methodology doesn't really change so long as the epidemiology for those impacts is available. It's pretty straightforward to consider those, and I think we would like to do that as well. It's just that within this context, we haven't done it yet.
Yes, I don't know if you can hear me. Hello?
Yes, we can. Go ahead.
Yes, I'm Kenan Al-Rishdi. I'm a part of the U-Tree Institute at University of Toronto. I was wondering if it would be beneficial to look at the gender groups among the data set, see who's more vulnerable to certain pollutants, be it men or women, and who's more responsible to generating more pollution, and whether this is beneficial from a health standpoint.
Robin, you have thoughts on that? I think it's an interesting question. I'll start, and maybe Robin can chime in. The problem is that once you analyze things within the confines of the computational grid that we have, which, at best for us, this is an exceptional data set of 1 kilometer, this is still really coarse. And within that 1 kilometer, you're probably safe to imagine that you have as many men as you have women. And somehow I don't think that you can really tease out signals that would provide the type of information that you're looking for in that regard. Maybe I'm wrong, but that is one complication that I can think of. What do you think, Robin?
Yeah, I mean, partially I think here, at least with environmental inequality, there's the resolution and also data availability is limited. Like, there have been specific, very, very high resolution studies done in, say, Hamilton, where they've had pregnant women wear backpacks all day to track their locations and their relative concentration. But I think, like Amir said, at a 1 kilometer grid resolution, you're losing a lot of that information. And also in previous studies, there there's a lot more mixed messages around inequality and gender. Like it seems to be driven a lot more by race and income than it does by other socioeconomic factors.
Oh, well then that.
So one thing that I do want to ask the CANUE community is that again, if you see, because the value of any possible value of what we do is if it can be properly linked to the downstream applications or upstream applications. So if you have thoughts or ideas of how this work can be improved or augmented to linkage with other areas, please let us know.
Yeah, this is Tim Takaro. One of the things I do is co-lead the climate and weather working group with CANUE. And I can think of a number of potential collaborations here with regards to the co-benefits in particular, and using future projections of climate change to show under different RCPs the benefits and accrual over the next several generations.
Excellent. So hopefully we can discuss those in more details sometime.
All right, we're at 1 p.m. exactly, so we'll conclude this webinar. Thank you very much, Amir and Robin. Excellent seminar, and this will be posted on the CANUE website.
Thank you very much. Thanks, everyone.
Thank you.